Alright, you guys, so in this video, we're going to go over this is the 4.1.3 practice. It's one of those ungraded worksheets that I can go over with you to kind of give you some more examples of the stuff you need to know. So in this one, we are still looking at confidence intervals for a single population proportion. So as we learned in 4.1.1, we do a z interval for single proportions because proportions are binomially distributed for the most part, as long as we have a large population. And we can approximate the probabilities of a normal distribution or of a binomial distribution using normal approximation. But we have some criteria that have to be met first. And that's what we have here. It's giving you some examples of some population sizes, some sample sizes, and some sample proportions, and asking us to determine if this meets the criteria to be able to use normal approximation and in a binomial setting in order to do our z interval, our z confidence interval. So basically there's three things we need to check. And I think they have two of them listed here. We need, in order to use normal approximation, np hat has to be greater than or equal to 10, as does n times 1 minus p hat. That's the criteria to be able to use normal approximation in any binomial setting. The other thing that we need to have here, which they don't list, is the fact that in order for a probability distribution to be considered binomial in the first place, the population size has to be at least 10 times greater than the sample size. And we talked about this a bit in the last video. The reason for this is because when we are sampling, we are removing subjects from the population. And each time you remove a subject from the population proportion is going to change a little bit. And so technically, that means that it's no longer independent, which means it's no longer a true binomial distribution. But as we learned when we first were talking about binomial distributions, we can ignore that fact if our population is big enough. If our population is big enough, then removing one subject or a few subjects from that population is going to change the proportion, but it's going to change it by such a tiny, teeny amount that it's not actually going to affect anything in the long run. So our general rule is that the population needs to be at least 10 times bigger than the sample we are removing from it in order to not skew that population proportion at all. So we're going to check these three things for these examples we have here. So starting with this first one, I'll go ahead and start with my population size. Is 100,000 greater than or equal to 10 times my sample size, 50? I'm checking this condition right here. All right, well, let's see, 10 times 50 is 500. So yes, 100,000 is greater than or equal to 500. So that condition is met. It is a binomial distribution. Now that we know it's a binomial distribution, can we use normal approximation? So we check n times p hat first. N is 50, p hat is 0.05. N times p hat then is 0.25. So this number needs to be greater than or equal to 10. Is 0.25 greater than or equal to 10? No, it is not. So this does not meet the conditions necessary in order to use normal approximation. So the answer here is no. Yes, there is one more condition that would need to be checked, but once I have a condition that's not met, we can stop there. All three conditions must be met. All right, next one, same thing. Compare the population size and sample size are the same as last time, so we already know that this condition is met. So let's check our if we can use normal approximation now. So NP, 50 times 0.38, is 19. Is that greater than or equal to 10? Yes, it is. Now we check the other side. 1 minus 0.38 is 0.62. And 50 times 0.62 is 31. Is that greater than or equal to 10? Yes, it is. So not only is this a binomial distribution, but we can use normal approximation here. All right, in this next one, you can see we have a sample size that's slightly larger. So is 100,000 still going to be greater than or equal to 10 times that sample size? Absolutely. 100,000 is greater than 600. Okay, so now that we know it's binomial, let's check our proportion again. And now instead of giving us p hat, they give us this x. So remember here, p hat is equal to x, the number of successes, over n, our sample size. So when we're asked to find p hat times n, p hat times n, or np hat, actually gets us back to x, the number of successes. That's actually a really neat shortcut, and if you remember that, np hat is the same thing as x, the actual number of successes. So I could use my 27 and my 60, calculate my p hat, and then divide by 60, but it's kind of silly because you literally divide by 60 and then multiply by 60, which gets you right back to x, 27. So is 27 greater than or equal to 10? Yes, it is. Now we check the number of failures. Well, I could do my p hat, 1 minus that, and multiply it by n. But what n times 1 minus p hat is, it gives us the number of failures in our sample. So if there are 27 successes and 60 total items in our sample, how many failures were there? Well, 60 minus 27 is 33. So if there were 60 items in our sample, 27 of them were successes. That means 33 of them had to have been failures. So even if I were to calculate my actual p hat, subtract it from 1 and multiply by n, you should get 33, because that's what this expression represents. And is 33 greater than or equal to 10? Yes, it is. Okay, moving along. Next one, same thing. I already know this is going to meet my population size, because again, our population size is 100,000, and this time our sample size is much smaller. So we are definitely have a large enough population. So we'll move straight to, or actually I'll just write down real quick, n is greater than or equal to 10 times n. That's good. So let's check our NPs. Our number of successes here is 2. So NP hat is 2. Is 2 greater than or equal to 10? No, it is not. So we cannot use normal approximation here. So again, B and C, I guess I should have written those answers were yes, yes, A was a no, and D is a no. Okay, moving on. The manufacturer of Vicious Victuals dog food want to know the proportion of dogs that prefer their product to other brands. They randomly select a sample of 589 dogs and present each dog with a bowl of Vicious Victuals and a bowl of another brand of dog food. On this sample, 374 dogs chose Vicious Victuals. All right, so N is 589, X is 374. We got some numbers. So part A, can we estimate the population proportion using the normal approximation to the binomial in the scenario? Okay, so A is asking us to do the same thing we did in number 1. So first we'll ask ourselves, is the population size greater than or equal to 10 times the sample size? Well, we can see our sample size here is 589, but they don't actually give us a population size, which is pretty common. We don't usually know the exact population size. So we have to ask ourselves this: is the population size likely to be greater than 10 times the sample size, 589 times 10? So do we think there are more dogs, or their population here is just dogs, than 5,890? Think about it. Are there more than 5,890 dogs in the world? It doesn't even say like America or a specific city. So I would say that's definitely reasonable to assume. Okay, moving on, we have to check our NPs, which N times P hat is X 374, which is definitely greater than 10. And then N times 1 minus P hat, number of failures. I can find that easily by subtracting 374 from the total sample size, which gives me 215, which is again definitely greater than 10. So yes, we can use normal approximation to the binomial in this scenario. All right, part B. What is the point estimate P of the population proportion of dogs that prefer vicious victuals? Well, the point estimate for the population proportion in any scenario is going to be P hat. P hat is the proportion within a sample. And to calculate P hat, we take the number of successes, X, divided by the total sample size, N. And we have those numbers over here. So I'll just take 374, divide it by 589, and I'll get my sample proportion, which we're going to use as a point estimate of the population proportion. That is 0.635. So there's my P hat. Moving to part C then. What critical Z value would you use to conduct a 95% confidence interval of the population proportion? At this point, you should be memorizing these numbers. The critical Z value for a 95% confidence interval is always 1.96. D. Calculate the standard error of the population proportion, SE sub P hat. So we have a formula for SE sub P hat. I'll use this space over here to write it down. So the formula, actually, first of all, they asked not just for SE sub P hat, do they? Oh yeah, they do. I'm getting ahead of myself. The formula is square root of P hat times 1 minus P hat all over N. And we just calculated P hat, and the part above it was 0.635, and we know N from the beginning was 589. So let's plug those in. 0.635. 1 minus 0.635 would be, let's see, 0.365. And N, our sample size, once again, is 589. So we multiply on top, divide by 589, and then square root. Oops. So I get 0.0198 for my standard error. Which brings us to part E. Calculate the margin of error, M, for the 95% confidence interval for the population proportion. So M, the margin of error, is that thing that we add or subtract when we're creating our confidence interval. So from our confidence interval equation, we know that the margin of error actually is always Z star times the standard error. Z star times the standard error, and in this case, we're looking at the sample proportion, which we just calculated above. We know Z star is 1.96 because we're calculating a 95% confidence interval, and we just found in the part above that our standard error for this sample proportion is 0.0198. So quick multiplication on my calculator tells me that my margin of error is 0.0388. So that's the number that we'll add and subtract from our point estimate to get our confidence interval. So next part, of course, is to do that. We take our point estimate, p hat, and add and subtract our margin of error, z star times the standard error of p hat that we just calculated. P hat, again, which we found in part B, was 0.635. So we're going to add and subtract from that our margin of error, z star times the standard error, which we calculated just above there, 0.0388. So I'll subtract to get my lower bound, which is 0.59629. And add to get my upper bound, which is 0.67371. And there we go. Now we can say we are 95% confident that the true population proportion of dogs who prefer vicious victuals is within these two numbers, is within this interval. Okay, the next part here, we're going to do the same thing, but now for a 99% confidence interval. So once again, you should have these numbers pretty much memorized by now. The critical z star for a 99% confidence interval is always 2.576. A lot of times you'll see in Apex, they like to round that to 2.58, which is fine. Okay, now it says calculate the margin of error for the 99% confidence interval. Basically the same thing I did above here in pink, but now my z star is a different number. It's still z star times se sub p hat. That's my margin of error. But now my z star is 2.576. My standard error, though, is completely unchanged. So when I take that standard error, 0.0198, and multiply by our new z star, we get a new margin of error, which is 0.051, which we can then use to calculate our 99% confidence interval, the same way I did in green above here with my new margin of error. It's still p hat plus or minus my z star times the standard error of p hat, just like it always is. But now my p hat is unchanged, but my margin of error is changed. We calculated that above in purple. So I subtract to get my lower bound, which is 0.584124, and add to get my upper bound, which is 0.685876. Remember, you can pause these videos to try to figure out how I get these numbers on your own before I reveal them. It's the beauty of having a video. Pause it, figure it out, and then check your work. Okay, it's the whole point of having these. All right, moving right along. J, use your graphing calculator now to construct a 90% confidence interval for the proportion of dogs who prefer vicious victuals. So let's get out our calculator. In the 4.1.1 video, we talked about how to do this on your calculator. Turn it on first, of course. We go to the stat menu, go over to tests, and we're looking for, we have a one sample proportion, and we're doing a z interval, not a test, not a hypothesis test, a confidence interval. So one prop z interval, there it is on my calculator, it's option A. And when I go in there, it just automatically asks me for the information it needs. I can scroll up to see what all that was. So let's see, X is 374. N is 589. And my C level, they said to do a 90% confidence level, so I'll change that to just 0.9 and hit calculate. There it is. There's my confidence interval as well as my p hat. So I can write that down. It went from 0.60235 to 0.6676 using my calculator at a 90% confidence interval though. All right, next, number 3. Suppose you want to estimate the proportion of voters who will vote for you in an upcoming mayoral election. In the previous election, 62% of the voters voted for you, and you suspect the same proportion will vote for you in this election. A, what is the minimum sample size you'd need to know if you wanted to construct a 95% confidence level with a margin of error no greater than 3%? Okay, we talked about this in your notes. Using the margin of error formula, we can find this number n, which also, and then the book Apex, I guess, also gave you the inverse of the margin of error formula, so we can calculate n more directly. That formula is n equals, that's a z, let me just correct that, that's all right, z star over m, all squared, don't lose that square, times p star times 1 minus p star. Okay, so all I need to do then is plug in what we have. So we're looking for n. We're doing a 95% confidence interval, so z star is 1.96 like always. M, our margin of error, they say is no greater than 3%, so I'll put 3% here as a decimal is 0.03. P star is what we think our proportion will be. It's our guess, which in this case, you're saying we're guessing that the proportion will be the same as it was in the last election, 0.62. And 1 minus 0.62 is 0.38. Oop, drop my square. Don't drop your square there. Okay, so go ahead and start simplifying that. Starting in your parentheses, that fraction, 1.96 divided by 0.03 is 65.333 repeating. I'll go ahead and square that right away to get 4,268.444 repeating. And then we multiply all those numbers together to get that n needs to be at least 1,005.6455. And of course, we can't sample a fraction of a person, so I would increase that by 1. We always round up when we're looking for a minimum because we can't go lower than the absolute minimum. So we have a minimum sample size of 1,006. Part B, you want to know whether the previous election's results were still valid as an estimate of the population proportion. What's the safest estimate for the minimum sample size? So in other words, in this part, we don't want to use this 62% anymore. Instead, we want to be as conservative as possible. And as we said in the notes, when you're looking for a sample size based on a margin of error and you want a extremely conservative answer, we're going to let our P star, our guess for a proportion, be 0.5. In other words, to get your most conservative minimum sample size, we guess that the results will be exactly 50-50. So we're going to do the same thing now that we did before, but now P star will be 0.5. So Z star is still 1.96. M is still 0.03. But now P star is 0.5, which means 1 minus Z star, or P star, is also 0.5. In our book, in our notes, we also noted that this equation, when we're using the 0.5 conservative choice, that n actually equals Z star over 2m squared. It kind of reduces there. Watch, I'm going to do the same thing on this side with this reduced version, and you'll see it gets me the exact same answer. So it's not a big deal if you forget about this. Oops, 2 times. There it is. All right. So let's try both. They should give you the exact same answer. Okay, so on this one, I'll divide on this fraction, square, and then multiply by 0.5 twice. 1.96. In fact, I'll do it on here so you can watch me do it. On, clear. 1.96 divided by 0.03, and then squared, and then times 0.5, and then times 0.5 again. We get 1067.11 repeating. Watch if I use the alternative formula. You should get the exact same answer. My denominator here is 2 times 0.03, which is 0.06. So I divide and then square, and voila, I get the exact same answer, 1067.11. So that's our minimum, but of course we cannot survey a fraction of a person, so we have to round up. We never round it down because this is our minimum, which means we cannot round down. So we need to survey at least 1,068 people to get a conservative answer. So we can ask ourselves here, looking at the 2 possible sample sizes, is it really going to be that much more work when we're surveying 1,000 people? We can do an extra 62 people and get a more conservative result. Probably not that big of a deal when you're already doing 1,000 people. All right, and that's it for 4.1.3.